So I'm thrilled that we have Steve Garwin joining us this week. Steve has more than 33 years of experience as an exploration geologist with large and small mining companies and is one of the leading authorities on porphyry, epithermal and Carlin-style mineralization in the circum-Pacific. So it's awesome to have Steve here to share some insights on the importance of geological mapping, drill hole logging, and 3D geoscientific data integration in the exploration and resource expansion of porphyry copper gold deposits. So thank you so much, Steve, for joining. It's amazing to have you.
Thank you, Jessica. Yeah, that's quite a mouthful of a title.
It was.
It's hard to say that all in one breath. You'll have to come up there halfway through. Yeah, I think some of you, I've been giving this sort of talk probably since 2018. And it's just something that's near and dear to my heart. I think there's a lot of just good old-fashioned observation in geology that can be applied not only to porphyry coppers, but just about any type of deposit one would care to explore for. And it's using the geology and a lot of 3D visualization, which you still can do on a light table and in your head. But fortunately today we have software that makes things a little bit more easy for us to do. But there's nothing really anything new here. I'm going to give you two examples of large porphyry copper gold deposits where this works very well in not only exploration, but resource expansion. All right, so how do we go from an outcrop like this into something that could become a drill target and then further into a resource or a reserve? And that's kind of what this talk is about. There's an outcrop of what we'll call B-type quartz veins. These are just sheeted, granular, sugary quartz veins which have center lines filled by sulfides. And we go ahead and make a map. On the left, you see the abundance of these veins, percentage, volume percent, or so many veins per meter in the stream. We then make a series of level plans and cross sections, of course, after we've started to drill. And ultimately, we can turn this into a 3D model. So that image on the far right is showing a slice through a 3D model that has the 0.9% copper equivalent outline with a broader halo of 0.3% and the direct relationship to greater than 5% B-type quartz veins. It's a linear relationship often. We can often plot this up and see the relationship of copper to vein abundance often exceeds 0.6, 0.7 out of a perfect 1.0. Not all deposits are like that, but the nice thing is if in this deposit, for example, there's a relationship of B vein abundance, quartz vein abundance to assay grade, that makes it very easy for us to target our drill holes, to predict grades before assays even come back. So the main bit of this talk today is we're going to talk about what a porphyry deposit is. Just very briefly, I know most of you guys already know that, but when I say a porphyry deposit, I want to make certain everyone understands what I mean when I say porphyry deposit. And then we'll spend a bit of time on what's called the Anaconda Method. This is a method that was developed in the 60s and 70s by Anaconda copper mining geologists actually for mining, and then it's been applied to exploration. And this method basically allows you to critically observe and record data in the field, be it in the outcrop or in drill core. And then how are we going to use this to visualize many different types of data from mapping, from core logging, to integrate into deposit models and exploration models. I'll show some examples of doing this from the giant gold, copper, silver porphyry system Alpala in northern Ecuador that's been recently discovered by SolGold, and the Cordillera copper gold porphyry deposit in northern Chile, which has been recently announced in terms of a resource by Hot Chili. And we'll take it all the way through from creek mapping, through drill core logging to 3D model and resource estimation. And then lastly, we'll conclude. So we've got about 50 or so slides. So this could take up to an hour of talking. I hope you stay around for it. We can have a discussion afterwards. I appreciate if we hold the questions until the end. So what's a porphyry? Well, generally, the porphyry systems are very large. They affect cubic kilometers of rock. However, the intrusions that cause this are fairly small. Like the finger on my hand, you might have a 500 meter to 2,000 meter sort of intrusion going down into a fairly large batholith at depths. This might be within 1 to 2 kilometers of the surface of the Earth, and the bottom of the batholith that it's capped into might be 9, 10 kilometers deep. The top of these cupolas, where the porphyries form around the finger, if you will, are typically 1 to 4 kilometers beneath the paleosurface. We typically have series of clusters of deposits like the fingers on my hand, but not all of them are economic. Porphyritic texture, well, that's why they call them porphyries, and it's telling you about a physical process that's occurred during crystallization from a magma chamber, and that most of these porphyry deposits are related to intrusions that have 40 to 60% crystals in a fine-grained ground mass. And that tells you that there basically was a pressure quench and a rapid ascension of magma out of the magma chamber into the cupola, and a rapid cooling and pressure quench from depths of several kilometers to within 1 to 2 kilometers from the surface after about 40 to 60% crystallization. So all that fine-grained ground mass is what's formed during that rapid magma ascent. And those crystals that were swimming around in the magma chamber, they came along for the ride, along with the copper and gold, which is sequestered out of minerals that might contain them in the magma, such as hornblende and mafic minerals, and sent into this fractured cupola and carapace that's full of quartz veins because there's a lot of silica and metals. So that porphyritic texture is a very important indication of a critical process that when you team together with fertile melt and a source of copper and gold can make a porphyry deposit. Often lightning strike more than once. We get several phases of intrusion that come in, and sometimes they're all within a couple 100,000 years. Other times they're reopening the intrusive contacts of older plutons and batholiths. Each intrusion phase often has a number of stages of hydrothermal alteration. We talk about central potassic, distal propylitic as early stages of alteration. We have later phyllic, intermediate argillic, advanced argillic phases. How do we get fluids into the rocks and the intrusions themselves and the adjacent wall rocks? Fracture permeability. These fractures are filled by sulfides and quartz veins that contain sulfides. Porphyries typically have metal zoning. The center of the deposit, which is typically formed early and hotter, is commonly rich in iron, such as magnetite. It can have copper, it can have gold. As we go a little further outboard, we get into a proximal moly halo out into the distal lead, zinc, manganese, gold, and silver annulus. And this is the characteristic metal zoning that most porphyry systems show over distances of 1 to 9 kilometers from the center of the porphyry. And fluid evolves in time and space, early hot saline fluids to later cooler, more dilute fluids. That's a picture of Batu Hijau, which I did my PhD on with Newmont and worked with Newmont for years prior to doing the PhD and thereafter. And that's a lovely picture. Batu Hijau is a large deposit in southwestern Zimbabwe. Mining began there in 1999. This picture is shortly after the commencement of mining. Mining is scheduled to go there about 35 years. So maybe in 2033, they should be finishing up or so. Okay, now the Anaconda Method. This is a method, I think it kind of changed my life, if you will. I was first taught this method or exposed to this method in 1996 at a course run at Batu Hijau where Marco Einaudi came and presented this. And he was one of the fellows along with a few other guys like John Prophet, Hunt, and Ware, and we'll talk about them, who developed this method in the 60s and 70s for the Anaconda Mining Company. And basically, it's very simple. We use colored pencils, all right? We use a lot of, it's like a painting. We have our maps, and we use a lot of color, and we use symbols. We don't put so much in the notebook. We want to be able to visualize what we're mapping and what we're logging. It focuses a lot on what's important. If we're looking for copper and gold, and the copper and gold is in sulfide minerals, and those sulfide minerals are related to the abundance of fractures or quartz veins, we log what's important. We quantify the strike and dip in mineralogy of these features, and we quantify the abundance measured by volume percent veins, or we can measure number of fractures across the dominant fracture set per meter, because these have a direct relationship to grade. So of course we look at, we use our Brunton compass, and we look at the relative cross-cutting features. We often, I'll show you, there's many phases of intrusion, and it's often hard to see all phases of intrusion cross-cut one another in a given drill hole or in an outcrop. But what we can see is that there's a vein paragenesis from early hot plasticky veins to later through going more brittle veins full of quartz to later sulfide-rich veins to veins that have halos of alteration. This develops early to late. So once we have a vein paragenesis, we can then work out intrusion A has been around for the whole party, okay? So that's the oldest one. Intrusion B come in and cuts the quartz veins, but is cut by the sulfide vein. So it came a little later. So through this vein paragenesis, we can then determine an intrusive paragenesis, which is a direct relationship to the grade. I say it's like a copper party, all right? There's people that come early to the party, if it's a successful party, they want to bring a lot of the alcohol, all right? They bring the kegs of beer, they bring the crates of wine, and the later intrusions come along and they're enjoying the party, it's already in full swing, but they might bring only a few bottles of wine or a 6-pack of beer. And that's still okay. They've brought less copper and gold to the party. The intrusions you want to watch out for are the very late intrusions. The ones that are upset, they missed out on the party, maybe they don't like the noise and they call the police, okay? These are the barren intrusions to dilute your ore body. So the vein paragenesis helps you determine the chronology of intrusions, very important. Okay, so we do a lot of mapping. Yes, we can do numerical mapping. We can do things with computer databases. It's not mapping versus computerized spreadsheets, it's combining the two. The key thing about this whole method is a geologist who draws what he or she sees has a much greater flexibility than having to fit it into A, B, C, or some column you tick in a spreadsheet. Not that you can't have spreadsheets in this, and we do, but you have to make these spreadsheets fit the rocks, not the other way around. So, we make fact maps. We put a lot of data on the maps. We try to use colored pencils. We use numbers circled saying that's a rate, that might be the ratio of the average thickness of the vein divided by the average spacing of the vein, things that we can take in visually. We try to minimize the amount that goes into the notebook because the notebook's hard to share. The maps can be scanned, they can be georeferenced, they can be stored in fire-safe cabinets, but even if the map burns down, you've got a GeoTIFF scan map of it. So very useful. We use standardized colors, so you don't even have to speak the same language. I show my map to someone in Ecuador. We agree on the legend to begin with. We do not have to speak Spanish or English together. It's like a painting. A picture is worth 1,000 words. And this has been developed by the Anaconda geologists in Chile, in Yarrington, Nevada in the 60s, and people like Marco Einaudi, John Prophet, John Hunt, Bill Atkinson, and John Dillis should get quite a bit of, we should just acknowledge that they've made a significant contribution to exploration and the science of porphyry deposits and even mapping in general. And I can give you a manual, which could be available on request. I'll send you a PDF manual that goes through this whole method if you like. I'm going to quickly summarize the method just a little bit to give you a taste, and then most of this talk will be showing about how we use the data that we collect. This is a face or trench map. You could be mapping a wall to a drill pad. You could be mapping a stream, and we just project it from a bird's eye view. We're looking down, okay? That's simple because then we can have multiple benches all in the same map, just staggered, but we're looking down. And what this map does is it has a rock side, which is on the right-hand side of this particular map, and an air side, okay, which is outside of the rock where you're standing and mapping on the left side. And you can fit a lot on this map. The thing is we have colors. We have colors, things like brown for goethites or sericites. We have yellow for pyrite, red for chalcopyrite, orange for quartz veins. We have pink salvages of the veins that are for K feldspar. You agree on what the colors mean. You can see the little dots show that those sulfides or oxide minerals are disseminated on the rock side. We see the orange quartz veins that have red dots on it. That means there's chalcopyrite in the quartz veins, and we take the salvages of those veins off onto the air side and see that they've got K feldspar salvages. On the northern part of the baseline, we see we've got a number of vein, quartz chalcopyrite veins, disseminated sulfides, and magnetite. We have a blue fault zone there. And south of that, we have a lot of pyritic material. We have a different phase. We have and we can see that there's a lot more quartz sericite pyrite alteration with those halos of sericite on the D veins to the south of that fault. So, this is very easy. For things you can't show visually, you have notes, as we always do. It's a tonalite, it's got so many percent quartz veins, etc. But you just continue to do this, and I can do this at 1 to 5,000 scale and do 700 meters to a kilometer a day in streams. Okay, that's the sort of, it takes a bit of time. Once you get used to it, you can break this into series of layers, for example. So here you might have one layer that would be, in the upper left there would be rock types. We have an andesite and a fault tonalite fault contact against a tonalite porphyry, which then has an intrusive contact against a quartz diorite. We can see the orange quartz veins. We can see the blue faults. We can see there's even magnetite and biotite veinlets. You can show your strikes and dips. That might be a base map, a one layer. We might have a piece of film on top that's transparent, mylar, and then we can go ahead and put in our alteration. We can show the fracture or vein controlled alteration. In brown would be sericites. In dark green, olive green would be biotites. In pink would be K-feldspar. And then we can see the dots, the disseminated alteration. Another layer on top of that, if we're in oxidized rocks, would be limonites, goethite, jarosite, hematite, or leached fugs. Or if we're in sulfide rocks, that would be chalcopyrite, pyrite, bornite, molybdenite. So again, these layers go one on top of the other, and you can see the strong relationship of the veins to the alteration, of the veins to the oxide minerals. We can see where the glassy limonite is in red. Okay, that's telling us that the chalcopyrite there has had just a little bit of oxidation, and you have an in situ limonite. Okay, and it's that glassy pitch limonite. It looks a bit like a beer bottle in terms of its kind of conchoidal fracture and resinous vitreous texture. So this is just basic mapping. And it's something that most people know how to do. It's just not as commonly done these days, and it's not taught in university the way I think it used to be, for example. Okay, so that's fine. It's not a mapping course. You can get the manual from me if you like. Many of you already know this method. Here's what we did with it when I took my first course in this in 1996. This is at Batu Hijau, which is a very large world-class porphyry copper gold deposit, which I've been involved in. This is a drill pad number 86. It had about 10% veins, which you can quantify by measuring the average thickness of the vein divided by the average spacing between the veins. And you might have one set with 4%, another set with 6%. We add up the two sets, we get 10% for this outcrop. So what we did is we mapped the drill pads, all right? And then we went ahead and basically for each drill pad, we put a number. That was the total percent of porphyry style quartz veins. A plus B veins, if that means anything to you. So that's fine. And then we went ahead and contoured that. So in this orange outline here on the right, you see abundant quartz veins. That's more than 5 volume% quartz veins. Now those pink outlines are the surface expression of the tonalite porphyries. Right. You can then see the black outline, ruled outline. That's the 0.5% copper outline at 307 meters above sea level. Well, the top of this ridge was about 650 meters above sea level. So that's projected down to a datum, a few hundred meters below surface, and that gives you the outline of a 0.5% copper. Please observe how well that correlates with the 5% quartz veins measured at surface. So you drill the 5% quartz veins in this deposit and you will outline the 0.5% copper. Many systems, in some systems it's 1% quartz veins, 5%, if it has a lot of veins, very useful. So you can outline the ore body in many cases, if it's not covered by post-mineral cover, by just mapping the A plus B type porphyry quartz veins. And you can see the 3 drill holes there. The first holes, 1, 2, and 3. And then that outer dashed green line is the limit of secondary biotite. This is hornblende typically being replaced by shred-like or shreddy biotite. Fine. Okay, so that's kind of the importance of mapping. I'm using quartz veins as an example because it's pretty simple to get that right. So let's show an example of the application of this method to Apala. And I was fortunate to be involved very early on with the discovery of Apala, and still am involved with this through SolGold, and it's turned out to be one of the larger copper gold porphyry discoveries in the last decade. And let's show you how we use the Anaconda method and the results we have. And we started on this almost from the beginning. So there is an outcrop. That is the discovery outcrop, which was found in May 2012. Okay, and it took about 5 drill holes to realize that this thing was quite big and went down a long ways, well over 1 kilometer from surface. And what we have here is basically what the discovery outcrop was an 80-meter wide zone of about 2% by volume sheeted veins that look like this. One of the first things I did when I was involved with the project, it was drill hole 6 or 7, was say, let's start doing some mapping. The guys have done a good job of quantifying the amount of veins and channel samples, very nice, which are even being used in the resource, drill resource estimates using the channel samples. We went ahead and had a mapping course. You can see here, this is an example of some of the rock saw channel samples results that would get anyone fairly excited. 33 meters at 0.65% copper, a gram gold. 54 meters at 0.3 copper, 1.4 gold. This is a lot of phyllic overprinting to planar B-type quartz veins hosted in the stream, which is basically all sulfide. Yes, they're good results. You can see some of these drill holes exceed 1.5 kilometers at almost 1% copper equivalent. So it's a pretty good deposit. And this is stacked up against other deposits that are well known where drill hole data was published. So this is one of these charts that say, me too. Look, our prospect's really good. Look at those good results compared to everyone else. And of course, once the deposit gets quantified and a resource number gets put out, these drill hole intercepts become less important. But it is good, I mean, to know, have an idea of what they mean before you put out the resource, of course. And this is what gets exploration is so excited. 1.5 kilometers at a % copper equivalent. So shortly, one of the first things we did as a team in terms of the geologizing was to do the Anaconda mapping. And the guys did this and they got very excited by it. And they said, well, why don't you just start doing it? And they said, well, we're going to do it at 1 to 500 right in the discovery area. And they made this map just as drill hole 9 was beginning. Drill hole 9 is a planned hole. I mean, now there's hundreds of drill holes for 250,000 kilometers and the guys have done an amazing job. But this is the first geological map of the discovery area. The discovery outcrop is right in here. If you can see my cursor, near drill holes 5 and 1. And they put it in just as drill hole 9 was starting. And so what we have here is the streams. You can see the scale. It's not very large. This took, by the way, 3 geos about 4 to 5 days. So let's call this 15 man days to map this area at 1 to 500. They could have done it. They could have done it 1 to 1,000, 1 to 2,000. They were keen. They did it 1 to 500, and they broke out some faults, a series of dikes, 3 different types of dikes. Some that were clearly old because they were altered and cut by these planar through-going porphyry B veins. Some that were altered that truncated those same veins, and some that were very weakly altered, seemed to be very late. So at least 3 stages of intrusions. Very important. They mapped out the abundance of those B-type veins. 2% in yellow. Well, sorry, let's see, I have to read my legend. 0.5% in orange, 2% in the green outline, and 5% in red, and 20% in purple. So the discovery outcrop of 80 meters at 2% is right in here. Well, clearly this was open because this is just the exposures are only in the streams, not in the jungle covered hills. And we could see it was open to the north and it was certainly open to the southeast. So the geologists went ahead and planned a hole here, B prime. That hole is still the best drill hole the entire project, 1.6 kilometers at 0.6 copper and 0.5 gold, including 570 meters at a % copper and 1.2 gold. So that's just basic mapping. Didn't need geophysics, didn't need geochemistry, really just mapping the B veins. And they did the similar sort of thing for the abundance of chalcopyrite and abundance of pyrite, and they did the chalcopyrite-pyrite ratio, which also indicated that it was open to the southeast, and that again is that stunning drill hole. So very simple mapping, just mapping the abundance of these veins contributed to the continued, well, the discovery of the high grade portion and some of the best drill holes in the project today. All right, so we'll take this a little further. So we're talking about veins. So here is a cross section showing drill holes color coded by those B vein abundance. Purple is greater than 10%, red is greater than 5%. Color coded in everything done by hand originally. Cross sections done by hand for rock type, for vein abundance, for sulfide abundance. We made a series of level plans. We stitched them together. And then ultimately, of course, we went into SURPAC and then Leapfrog and made 3D models of the system and found that the veins were incredibly accurate, even down to 0.5% as an envelope in predicting where the ore is. And yes, there is a vein paragenesis, which isn't really the focus of this talk, but we have early unidirectional solidification textures, USTs, expressed by late stage magmatic quartz and magnetite that then get cut by younger vein sets, including these chalcopyrite rich C veins. We have late bornite pyrite veins as well. We have evidence of earlier A and B type veins in quartz in an early intrusion that are cut by a later intrusion, which then the contact itself was cut by later pyrite chalcopyrite veinlets called CD. So this is partly how we develop this paragenesis. This late intrusion is generally less than 0.2, 0.3%. This early intrusion is commonly greater than 1% copper. And we're showing you a style of veins here, late chalcopyrite bornite on fractures, the standard sort of B vein stockworks, late D veins, which are characterized by pyrite with halos that are 5 to 10 times wider than the pyrite veinlets, where the mafic minerals and chloride has been destroyed and replaced by sericite and illite, classic D veins. So we developed a vein paragenesis from early high temperature, iron-rich veins to slightly lower, lower temperature, later transitional veins. All these veins color-coded in blue, these are the guys that brought the copper and gold to the party. And there's all sorts of names there and letters, but really copper saturation happened after the earliest quartz and magnetite veinlets in the form of mostly chalcopyrite and pyrite, then transitioning into later pyrite bornite veins and peripheral intermediate sulfidation, base metal bearing veins, quartz, calcite, and hydrite, glenus, phallerite, pyrite, and some gold. So from that vein paragenesis, we're then able to work out an intrusion paragenesis, if you will, from the host rocks, which are volcanic and volcaniclastic rocks of variable grade, pre-mineral pluton, we call it diorite 10 just because that's fairly early. As you get to higher and higher numbers as you get later, D for diorite, quartz diorite, T for tonalite. And so we can see it's all about these QD10s. They're the ones that brought the copper and the gold to the party, most of it. They probably bought 80% of it. These subsequent phases probably contributed to about another 20%. These late phases, very low grade, and fortunately, volumetrically very small, these post-mineral dikes, which are barren. So there's not that much dilution in the system. And so it's just working up which intrusions by composition, we can call them D, Q, D, or T, and the time relationship with respect to the vein paragenesis. And you'll see that there'll be a direct relationship to grade. So there's a cross section on the left there, looking towards northwest. And then you can see the different colors indicate the different intrusive phases. The wall rocks, V, volcaniclastics, BX is a late hydrothermal breccia. You have the yellow D10, so that's kind of a pre-mineral intrusion that focused the mineralizing QD10s, QD15s, D15s, all the way through to the 20 series intrusions. And you can see the 0.9% copper equivalent is focused on the D10 wall rock to the QD10, and the 0.3 drifts out and kind of forms a carapace and halo to the combined intrusions. And that breccia is late and contains fragments of intrusions and fragments of veins, so it came late to the party. We can see if you go ahead and bin the different rock types by copper grade, you can see the story I've been telling you. Copper on the top, you've got your host rocks, volcanics, volcaniclastics in green, the pre-mineral intrusion, D10, the causal intrusion, and then a steady drop in copper and gold grades. And all of these intrusions, they all came in within, within the error, a 2 sigma error resolution of dating, all came in within probably 800,000 years or so. Okay, start to finish, plus or minus 800,000 years at 2 sigma uncertainty. But it's all about the earliest intrusion and then dropping away from there. So let's go ahead and put this together into something to share with you the geometry of the system. So note the scale here. At a 0.2% copper equivalent cutoff, we've got a strike length of over 2 kilometers. At a 0.45% copper equivalent, almost the same. At a 0.9% copper equivalent, you're getting into something that's more like 1 kilometer by 600 meters. And that's the cutoff grade. You'll find at 0.9%, the actual average of that portion that's above 0.9 is a closer to 1.5% copper equivalent. So this system is pretty much now, after 250,000, we're up around 250,000 meters of drilling, is pretty much confined. It is open a little bit at depth, but that's pretty much what we have. And we'll look at this in cross section, long section, and even a level plan. So what we have here on the far left is a hand-drawn section. We did all of this initially, everything was by hand, sections and level plans. And then we interacted with SURPAC models, and now we use leapfrog models. We have exclusively for the last few years. We're still drawing things by hand and comparing it to what the model says. And if we don't like that, we then tweak the model. We work it, backwards and forwards. The model's great because it's clicking to drill holes, whereas these sections, of course, are projecting the drill hole data to sections spaced about every 70 meters. So again, we're keeping the geology in this. And some of our early leapfrog models were horrible. They just looked like bubbles. So we're getting happier with this, and you can see the 0.9% outline in black and the 0.3% copper equivalent in blue and its relationship to the geology. On the far right, here is our molybdenum model, and this is quite useful. The core of the deposit, the high-grade core of the deposit, has got less than 10 ppm molybdenum. But you can see around the outside, still in pretty good grade, but in going out to 0.3 and even less than 0.3, we could go from 10 to over 40 ppm molybdenite, or molybdenum, I should say. The neat thing is that geologists, their eyes are as good as 10 ppm moly. They log where they see presence or absence of molybdenite on fractures. And if there's enough, they might say 0.1% molybdenite. But the point is, whenever these guys have said, hey, there's moly on fractures, usually we get above 10 ppm, sometimes down to 6 ppm moly. And why do we care about that? Because it's a perfect halo. If you were drilling from this legend down through to the northeast, you'd go through an anhydrite moly fracture halo before you got into the high-grade core of the system, and then you drill back out. So this is great. If you're in molybdenite fractures and drilling into a porphyry system, in a fairly oxidized system with copper and maybe some gold, you keep drilling until you get to the high-grade core and then come out the other side. On the left is, again, this quartz vein, these planar through-going quartz veins that I showed you pictures of, the B-type veins. They model incredibly well. So there's 0.5% in blue, 2% in green, 5% in, I guess that's red, 10% in purple. And look how well the 5% veins agrees with a 0.9% copper equivalent. Really good. And so anytime in this system, you start hitting above 0.5% B veins, you're on the fringe. Keep going. This is the chalco in the middle. This is the chalco-pyrite ratio. The guys log volume percent chalcopyrite, volume percent pyrite, and then they make a ratio of that. This is visual logging with a 20x hand lens. And this is how predictive it is. So that's 1 chalcopyrite, 0.5 is 1 chalcopyrite and 2 pyrite. 1 to 1 would be 1 chalcopyrite, 1 pyrite. So you see the good relationship of any time you get greater than 1 chalcopyrite to 2 pyrite, you're getting into it, just like you are with 0.5% veins. Once you get above more chalcopyrite than pyrite, you're into the high-grade core. Here you see these little bubbles of 0.3% visually estimated bornite up top, associated with advanced argillic and phyllic alteration, and a little bit down in the core of the system or up above the core of the system. Most of our bornite comes late. It's not early high temperature bornite magnetite, it's later high sulfidation bornite pyrite. So now we go ahead and we've got the geology model on the left with the copper grades just for reference. And then on the right, we have the pyrite model. This is visually estimated pyrite. And you can see there is a classic pyrite halo at greater than about 2.5% pyrite up to 5% pyrite as a cap. And down in the core of the system, typically we have about 1 to 2% pyrite. So even the core of the system has pyrite, but more chalcopyrite. It's a chalcopyrite porphyry. Alteration, this is mostly from visual logging. I'll show you another example later from calculated mineralogy for determining chalcopyrite-pyrite ratios and alteration assemblages. But we can log epidote replacing mafic minerals. We can log the abundance, epidote replacing plagioclase and epidote veinlets, and secondary biotite, shreddy biotite replacing hornblende. We can log that very simply, and we can see that the higher grade portion of the deposit forms on the transition zone from the core of biotite alteration or potassic alteration going outwards into an epidote halo. And something we've, and these are quite old slides, but something that we've found since then is that there's an actinolite zone, an inner propylitic zone of actinolite, higher temperatures, typically above 280 degrees, as you go from epidote into biotite. But again, from our paragenesis of veins and related to sulfides, we know that the early alteration, characterized by central potassic and more distal actinolite and epidote propylitic, the copper tap hadn't turned on. It was mostly magnetite and quartz. The copper tap turned on later, associated with chlorite sericite clay alteration, quartz sericite phyllic alteration, advanced argillic, but particularly the copper in chalcopyrite and pyrite is associated with this blue chlorite sericite alteration zone, which has overprinted the edge of the potassic zone. And as you can see, the grades go all the way to surface in this one section. So it's clearly not remobilizing from the potassic. If you have this style of alteration, you will even get, since this is a very mega dike sort of swarm controlled deposit, you'll get ore grades out into even chlorite grade propylitic. But typically it's related to temperatures of less than 400 degrees Celsius when you're turning on this sort of chlorite sericite magnetite pyrite stable overprint to potassic and propylitic assemblages. You even get specular hematite and magnetite going to hematite, non-weathering hematite, hydrothermal hematite during this time. And then subsequently, as the system cools further, you get the bornite pyrite associated with the phyllic and the advanced argillic alteration. And we've got some pretty pictures there, just to say that we did look at the rocks. But the point is that the ore zone here is not all about the black and pink rock. It's not all about the potassic zone. It's about the gray green rock. It's about the chlorite sericite clay alteration. So not all porphyries behave the same. Some porphyries, it's all about the potassic zone, high temperature and early. But many porphyries, particularly those that are gold rich, it's all about kind of the transitional assemblages, the chlorite sericite or the phyllic. That's when the copper trap and gold turned on. This is a long section, all right? So you can see, just to make certain you get the scale on this, that each box is 750 meters by 750 meters. So that's almost 2 kilometers beneath surface, all right, in the bottom of this section. And you can see we have this sort of the green volcaniclastic rocks as host rocks. The D10 is the pre-mineral intrusion, the pre-mineral diorite invaded by the QD10, QD15, and then subsequently this D15 coming up and kind of stoping out and making a deposit into a bit of a pendant. So we can see the 0.3% copper equivalent and the high grade pocket associated with the early caudal melts, getting medium to lower grade with the D15 series. And look at the molybdenum jelly donut. Look at that moly halo. This is the long section. Isn't that fantastic? What a great way of predicting when you're getting towards the high grade core of the system, just by looking at molybdenite ion fractures. There's another long section. Again, I'm showing you the relationship of the planar quartz veins. We'll call them B-type veins. An excellent predictive relationship to grade. And you log this as you go. You don't have to wait for the assays to come back. So when you have up to 12 or 14 drill rigs on the go and you have to wait sometimes 3, sometimes 6 weeks for assays, this is invaluable in helping you keep ahead of the drill program. This is the chalcopyrite over pyrite ratios that we saw. In blue, 1 chalcopyrite to 2 pyrite. In red, 1 to 1. And again, this high bornite, usually up higher with the phyllic alteration and advanced argillic, often related to this little nub of the D15. That D15 telescoped a lot of alteration and caused quite a bit of overprinting of the alteration related to the early 10 series, and also seems to have a fair amount of phyllic, high sulfidation, bornite pyrite associated with it. And when I say fair amount, it's really not, it's 0.3% bornite. That's not a lot. Locally, we might have zones, you could have 18% copper over a few 10 meters, and that'd be bornite dominant. But really, the copper in this deposit is largely from chalcopyrite. Okay, here's a level plan at 500 meters above sea level. So that's about 900. I'm getting confused. Yeah, I think that's about 1,100 meters below surface. And so here we can see the good relation agreement between the hand-drawn plan and the computer-generated leapfrog model. We can see the relationship of the causal intrusions and adjacent D10 wall rock to the high grade, and the elongate sort of dike-like nature to some of these intrusions, and the D15 kind of coming in at the bottom, as we saw in the long section and cross section, and around the outside. Again, you can see the molybdenite halo now in plan view. Very predictable. And then we have the quartz veins also showing a very good correlation. And we have the chalcopyrite-pyrite ratios. So in addition to determining out the chronology of the intrusions, we have the abundance of quartz veins, we have the sulfide abundance and sulfide ratios to help us vector in on the deposit. So this is a summary of just what I went through, and we'll arrange for a PDF copy of this presentation, as well as the videotape to be distributed. So even if I don't spend enough time on this slide right now, well, I guess you could always freeze it when you replay, but you can also get a PDF. Porphyries are strong systems. They affect a lot of rock in very predictable patterns. So we just need to be able to recognize those patterns to help us explore for them and increase resource once we find them. So that's the present resource estimate, depending on what cutoff grade you want to use. It's got a lot of copper and a lot of gold and silver. And what's really important, since this is going to be a block cave, is potential for an open pit, but really the core of this thing is deep. So we need the early payback, and that's where 442 million tons at 1.4% copper equivalent is going to be very important, and having that report to some of the early drawdowns in block cave. So you need the high grade to make this thing work. So it's not about the 3+ billion tons. It's really about the 500 million tons at high grade that make this thing work. All right, so that is Apollo, and that's still ongoing right now. PFS should be out by the end of the year. Now, more recently, I've been involved with Cortadera, and this is something that Hot Chili has found. Well, actually, they picked up the deposit, which was not well recognized. No resource was out on it. There was a small pit by a previous explorer. And Hot Chili has been working with it for a number of years. They have until they have a resource at Productora, which is about 14 kilometers to the west-northwest of Cortadera. And at Cortadera, the recent resources, the maiden resource was almost 500 million tons at about 0.46 copper equivalent, dominantly copper. You can see that this has got 1.7 million metric tons of copper. Combined with Productora, you have almost 3 million metric tons of copper with gold and silver and molybdenum as a byproduct. So this is interesting. This is in northern Chile, and there's separate talks on this if you want to learn more about the geology of this fairly exciting deposit, which is growing, owned and operated by Hot Chili. Now, I should comment that Cortadera resource is the maiden resource. It's getting larger. But I just want to use this as an illustration. You can see that there's about a 2.3 kilometer long zone that has 3 cuerpos, or 3 fingers kind of coming up along a camel's back, if you will. And we'll go ahead, and this is sheeted quartz veins with goethite and outcrop. You can see what some of this looks like in drill core and some of the assay grades that are accompanied with, again, sort of these sort of A and B type quartz veins in a rock here that's got a fair amount of phyllic alteration over printing albitized tonalites. This is just also another chart showing some of the drill results from Cortadera of Hot Chili in yellow. And again, some pretty good results, almost up to a kilometer at 0.5 copper and 0.2 gold. So not as much gold is Apollo, but significant, and including some nice intervals of up to 400 meters at 0.7 and 0.3. And more recently, an announcement of significant, this was just a few weeks ago, of 400 meters at 0.5 and 0.2. So there's some high grade portions to this. And now a similar sort of paragenesis. And we went with the same sort of style, 10, 20, 30, 40 series. The 10 series is the first intrusions, followed by subsequent intrusions. These are all roughly tonalitic in composition. And the wall rocks consist of volcanics and volcanosedimentary rocks and limestones. We even have distal versus proximal hornfells. And so you've got the thermal aureole of a proximal hornfells that might be bedding destroyed. It might have some garnet, skarn. More distal hornfells would be more like sort of chloritic, less biatitic, and bedding preserved. And so the earlier intrusions are higher in grade and they're adjacent wall rocks. And we can show this to you with the box and whisker sort of plot. Here we got copper, gold, silver, and molybdenum. Again, you've got the distal wall rocks, more distal, slightly affected hornfells, and weakly skarned, more proximal bedding destroyed, hornfells and skarn, 10, 20 series intrusions, bringing most of the metals to party, 30 and 40 series dikes. So, this is not uncommon, the sort of chronology relationship to grade in porphyry systems. So we'll take you through a quick model here, also done on Leapfrog, where we have 2.3 kilometers of strike length, which we showed you in the picture. And we see these cuerpos 1, 2, and 3, showing you the models of the proximal and distal hornfells in kind of blue and green. In magenta, the early and intramineral intrusions by these late dike swarms of 30 series tonalites and 40 series andesites. The neat thing about these dike swarms is they go for kilometers, and you can follow them into the systems commonly. And if you like the analogy of a pearl necklace with pearls along a string or beads along a string, these north-south crossing features help localize at least 3 sort of humps on a very elongate camel that's heading west-northwest. So this is a cross-section through the largest cuerpo, B to B prime, will be looking northwest. And this is just copper isosurfaces coated up. You tell Leapfrog to look along certain directions. You can see copper. This isn't copper equivalent. This is copper percent downhole with the histograms. And you can see there's a nice zone here of greater than about 0.3, 0.4. Look at the relationship to molybdenum. And we're also seeing a bit of a halo here. Molybdenum, there's more molybdenum here than at Alpala, but it's also making a halo around the center of the system. This is on the left is the abundance of quartz veins. This is what we call A and B type quartz veins. So the early high temperature quartz is a little more quasi-plastic, and the more later through going B type planar veins. And again, not a bad relationship to grade. Not quite as good as Alpala, because we do have some of these earlier quartz veins that mostly just have silica and magnetite and not very much chalcopyrite and pyrite. And you can see here this sort of high grade model of 0.4, only copper, not gold, and 0.1. So again, you can see the sort of nice geometric relationship we're seeing as we showed at Alpala. And then just put on the Molly halo to make that clear. This is a wafer thin slice of the geology. And you can see the gentle dips of the bedding to the southeast. Here, volcanics and sedimentary rocks, the proximal and distal hornfells and skarns, and the causal intrusions in pink and magenta, with the later lower grade dikes in yellow. And there's 0.3% copper, just to give you an idea. It is very much related to the 10 and 20 series and their immediate wall rocks. And the 30 series yellow is lowering the grade. So what we did here at Apollo, we also did what we call calculated mineralogy. But I haven't got great slides of that to show you right now, but I do have some nice slides. Scott Haley recently did the calculated mineralogy based upon the geochemistry and 4-acid digest and multi-element results for Cortadera. And the interesting thing is, you can then make some assumptions and calculate out what the silicate and sulfide minerals might be. So in this case, we went ahead and made some models, and we said, well, where there's more than 3% chloride and less than 10% mica, white mica, we'll call it propylitic. Well, that's green, all right? Now, where we have more than 3% chloride and more than 10% phengite or white mica, we'll kind of make that pale green. We'll call that cerussite chloride. And then there's this albite, greater than 30% albite, which here is in magenta. And that's partially overprinted by the white micas. We've got anhydrite, greater than 5%, as these kind of lungs, if you will, around the core of the deposit. And we have the phyllic, which is greater than 10% white mica and less than 3% chloride. So the phyllic stuff is gray, and the cerussite chloride stuff is greeny gray, all right? And so you can see there's a good relationship of the higher grades to where the rocks have secondary albite. We don't make that much potassium feldspar in these rocks because they're tonalite, so we make secondary biotite and secondary albite. And then that's also been overprinted by cerussite and cerussite chlorite. And so that's kind of the assemblage that's interesting. And then you can see how the moly fits with respect to that. Good relationship of anhydrite veins and anhydrite in the matrix to molybdenite. We see the same thing in many systems. And then here on the right-hand side is the chalcopyrite-pyrite ratio from the calculated mineralogy. And you can see again, here not quite as high a ratio as at Apollo, but chalcopyrite over pyrite greater than 1 to 2, right in the pretty much towards the center of the system. If we look at pyrite abundance, you see a very nice pyrite halo of 6 to 8% pyrite on top, and within the core of the system around 2 to 4% pyrite. So there's always going to be some pyrite in the system, and that's not uncommon. In many of the systems that have chalcopyrite and pyrite, you do get pyrite in the core. So very predictable and all quite useful. You do a lot of this through visual logging, and in this case, we're showing you how calculated mineralogy is useful as well. Quartz veins. We've talked about abundance of quartz veins. Now we can talk about orientations. So this is basically taking, these are oriented drill core. So the guys take alpha and beta and even use rocket launchers to measure the orientation of these veins. And they might say every 100 meters, let's make a stereo net and summarize what the average vein populations are. And maybe let's go ahead and take those average vein populations over each one signifying the kind of vein families over intervals of 100 to 150 meters downhole. And here's what you might get. So we're not plotting all the veins, of which there'll be at least 1,400 in this database, but here we're plotting about 120 of the vein sets. And you can see there's a strong northwest relationship, but there's also north-south and some northeast. And you can see there's also flat veins. So these are the Rose diagrams that are good for strikes. And these other stereo nets are looking downwards. You can see the vein poles. This is the perpendicular bit to the planes that are plotting the center are flat veins. Those that are around the outside are more steeply dipping. So there's some common families there. So you see there's flat veins. You also see that there's steep veins striking northwest, northeast, north-south. There we are. Now let's see where they sit though. This is what gets really interesting. So I'm kind of showing you a cross section looking towards the northwest. You've got the 0.4 outline in purple and the 0.1 as a reference, copper in yellow. And you're seeing little glyphs. These are little discs we make in Leapfrog, picking out the average vein population for every 100 to 150 meters, the primary set, and then the less dominant secondary set. So if you want to summarize this, you get something that looks a bit like this. And this is neat. Well, I think it is. Higher up in the system, you get more steeply dipping veins. All right. As you start getting into the guts of the system, and particularly the real high-grade zones, kind of below about 400 meters RL, you get a lot of flat veins. I've seen this in a number of porphyry systems. Right in the guts, into the cupola, or in the zone of high grade, you commonly get more flat veins than you see higher up, which are dominated by the steeper veins. So again, now we not just have abundance, but even the vein orientation can help us determine where we might be in the system. So we have a summary here of what I've just gone through as well. And again, you can read that later at your leisure. The point is that geology works. These systems aren't subtle. Picking out what's important. And for me, it's where the copper is. And you can even microprobe, and we do this early in many systems. Where's the gold? Is it with the chalcopyrite? Is it with the magnetite? Is it with the pyrite, or all of these? It's typically with the sulfides. So we want to know what we're looking for, and then we want to determine the geometry of what is the geometry of the shells that go further and further out to what might be the ore body. We want to go as far out as possible so we can tell if our drill hole or our outcrop is a near miss, or if we have to go this way 1 kilometer or that way 1 kilometer. So this geometry and geology works. And this talk isn't about geophysics, although geophysics are very useful, particularly if there's no outcrops. And so that's a separate talk altogether. Geophysics can be very useful. So don't mistake me. It's not all about the geology, but geology is very significant. So just talking about Cordillera, I just want to compare it. I've talked about Cordillera. It's a medium-sized deposit, over 3 million tons of copper when you combine it with Productora, getting bigger. And then there's Apollo, 10 million tons of copper or more. And I just want to compare the two because people, you put out an MRE or maiden resource estimate and people say, oh, that's what it is. And you even say, look, I'm not finished yet. I'm still working on it. That often benchmarks it in people's head. This is just my experience over the years I've been involved in this industry. And I want to show, and that happened at Apollo. The final resource is 3 times the size of the first resource. And I want to show you at Cortadera, here's Cortadera's sort of maiden resource at 0.2% copper outline projected to surface, roughly. There's the Apollo 0.2% copper outline after quite a bit of drilling projected to surface. You see similar strike extent, but Apollo at present, or Apollo constrained now, is wider than what's known at Cortadera. Apollo's resource, again, over 3 billion tons, or more importantly, almost 500 million at 1.4% copper equivalent. This is a long section. We showed you this long section for Apollo Cascabel in the early parts of this talk. This is a same scale long section for Cortadera. And you can see, okay, this section's a few months old, but you can see that there is some scope to add resource to Cortadera. This is a cross section, again at the same scale, showing Apollo's 0.9 copper equivalent, which would be about 0.5% copper, since it's so much gold, 0.3% copper equivalent, and then just copper, no copper equivalent on Cuerpo 3 on the right, 0.4 and 0.1. And the point being is that there's certainly room for more drilling. And now there has been some more holes on this particular section since, but there's still room to flesh out and grow Cortadera. Now, just to give you an idea again of scale, this is a plan map looking down at RTP ground magnetics, showing you a general circular degraded zone of magmatism in blue with little pinprick highs associated with each of the cuerpos, which is probably magnetite veinlets that we see. Then you can see the mapped hydrothermal alteration where magnetite's been destroyed and replaced by, well, I shouldn't say, this is an interpretation of a magnetic map at Apollo, same scale, thrown on top where there was clear sort of flat, magnetically flat quiet zone, which was interpreted to be magnetite destruction, compared to the actual mapping at surface of magnetite being replaced by pyrite with the magnetite and feldspar destructive phyllic alteration. That's the scale of a 3 billion ton ore body at depth, overlaid on the Cortadera system. Same scale. There's 0.4% copper equivalent for Apollo. So this is the things to think about. So if someone gives you a resource and they tell you they're still growing it, I think it's worthwhile listening to them. And when you're exploring, it's not all about necessarily having ore grades at surface. It's just about the size and coherency of the system, even though it might be fairly low grade at surface or your copper might be completely leached. One more slide along these lines of kind of size. This is how one uses the model. At Cortadera, in the southern area there, we can see a busy slide, but the 0.1% copper model envelope in yellow with black outline. And then again, that's about 2.5 kilometers there along the west-northwest strike. And then what we have, that's on a chargeability slice of about 300 meters below surface, so telling us where there's sulfide, particularly pyrite. And you see there's a pretty good relationship of chargeable rock to being on top of the ore body. And you see this molybdenum in soil at greater than 2.3 ppm. Fairly close relationship, a little off to the side, which isn't too odd because we talked about our molybdenum halo to the high-grade copper core. And that was what Hot Chili knew until about 2 years ago. Up to this, there were no soil samples north of this line here that says sort of currently drilling in here. So it was decided this looked interesting, this was open. Soil samples were extended across to the north because there also was known that there was this IP chargeability high. And sure enough, there's a moly anomaly at greater than 4.8 ppm. Different labs, different eras, so slightly different backgrounds. But again, here you have a chargeability high with a flanking moly zone, which prompted Hot Chili to go up and map the area, finding lots of epidote veins, 30 series dikes, some B veins, a bit more exciting. So this has led to an RC program, which will be followed up with diamond tails. So here's how we use one model made based upon just empirical data and employing it to go a couple kilometers to the north. And we'll see what happens when the diamond tails are completed. Looks like we're a bit higher in the system here, but certainly a porphyry system. So to conclude, is that the collection of accurate data is critical. Not just in doing good science, just in exploration. Finding out, knowing what we're looking for, finding out where it occurs, and how is it expressed in its geometry. Map more of that, get that data, use that predictive geometry to help target your exploration program. And keep updating it. You can take this all the way through to reserve modeling, metallurgical test work, and it's all applicable. And being able to visualize this in 3 dimensions is a very powerful tool. And you can do this the old-fashioned way with cross-sections and level plans, and or with Leapfrog, SurPack, other 3D modeling packages. And this is something that's been working forever, right? Since the 60s. And porphyries have the advantage of being a well-studied deposit model for over 50 years. But sadly, I don't think this is encouraged as much in our field schools anymore. And I've noticed there's a big trend to make beautiful geochemical plots and nice geophysical images because they look so sexy. But geology can be sexy. And I think as geologists, we need to push that and to make certain the people that are making decisions and for funding, for exploration, even in the share market, appreciate that geology does work. And we have to do it. I think it's up to us as geologists to push that and make it mainstream. And I encourage those geologists who have yet to use this Anaconda method to keep an open mind. And I call this an old school form of technology transfer. So I'd like to acknowledge the data and all the good work of SolGold and Hot Chili in this presentation. I'm talking now, but they're the guys that have done a lot of the good work. And of course, the Anaconda Copper Mining Company geologists for developing a critical way of observing and recording data in outcrop and drill core. Thank you very much.